Area between curves. Let's start with a brief review. Here we have a definite integral. The definite integral from a to b of f of x dx represents graphically the area between the function f of x and the x-axis on the interval from a to b. So let's go ahead and take a look at this on a graph. So let's say I have some function here called f of x defined on the interval from a to b. The definite integral from a to b of f of x dx would be represented as the area between the function and the x-axis that's trapped between x equals a and x equals b. I've gone ahead and shaded the region that this definite integral represents. Now let's take a look at the integral from a to b of the function g of x dx. So we have a different function here, g of x, and the definite integral is the area between that function and the x-axis on the interval from a to b. Once again, I've gone ahead and shaded the region that this second definite integral is referring to. But the name of the section is area between two curves. So let's say we are going to consider the functions f of x and g of x on the same xy plane, and we are interested in the area that's between those two curves, again limited by the interval from a to b. How would I go about finding that area? Well, I'm going to go ahead and shade that region that we're referring to. So here's the area that we're interested in finding, and hopefully you can kind of see how we are going to go about finding this the area of this region trapped between these two curves. Essentially what we're going to do is find this first area here, the integral from a to b of f of x dx, and then we're going to go ahead and subtract from it the area that's underneath the g of x curve. So if I take away that part below, then I'm going to have this part in the middle that's trapped between the two curves. So we're going to subtract the integral from a to b of g of x dx. And we know from our Calculus 1 days that there's no reason to write these as two separate integrals because they have the same limits of integration. So we can actually write this as the integral from a to b of f of x minus g of x, all as the integrand dx. Let's formalize what we just explored in that last example. The area between curves with respect to x. If f and g are continuous functions with f of x greater than or equal to g of x on the interval from a to b, so we do need to know that the function f of x is always above or on top of the g of x function, then the area between curves is given by the integral from x equals a to x equals b of f of x minus g of x. Or, a little bit more informally, we can think about that as the integral from x equals a to x equals b of the top function minus the bottom function. Now, if we go and take a look at this graph over here, this is slightly different than the one that we just looked at because this g of x function dips down below the x-axis. And what we should remember from Calculus 1 is that, area that's below the x-axis is negative. And in general, yes, that's true. But when we're talking about area between two curves, that's not something that we're going to take into account. We're considering the area between two curves as always positive. But we do need to have that understanding of area below the x-axis as negative for this formula to work out. So for example, if we take a close look at over here, if I go from A to this point of intersection right here, and I think about the integral from A to this point here, under the f of x curve, I'm thinking about taking all of this area here, and then if I subtract the area under the g of x function, then I'm taking away this area right here. So when the two curves are positive, it's a little bit more intuitive, like the last example that we looked at. But what about over here? So is it going to work out if I do the top portion So the integral under f of x over here, from this point of intersection, right, to b, the area under f of x is right here. And then I'm going to go ahead and subtract the area between the curve g of x and the x-axis. But what do we know about that area? We know that that area is negative. So right here, this area, we would consider that negative area. So when we subtract negative area, that makes it positive. So this formula does check out. It is going to work whether or not your functions are above or below the x-axis. We can always just stick to top minus bottom. So if both functions are above the x-axis, it just intuitively makes a little bit more sense. We're going to take this whole region and then subtract this little portion right here. But even if a portion of the graph is below the x-axis, when we do top minus bottom, it's finding this top area, the area above the x-axis, and then we're going to subtract negative area, and subtracting a negative makes it positive. So area between curves should always be positive. Let's take a look at an example. We want to sketch the region bounded by y equals x squared plus 2x plus 1 and y equals 3x plus 3 and find its area. So these problems really rely on us to know graphs of basic functions and be able to sketch them, because based on our formula, we're going to need to know which is the top function and which is the bottom function. So first we're going to start by graphing these functions. Now this first one is a parabola, and when we graph a parabola, we're interested in finding the x-intercepts. If possible, we're interested, and if necessary, in finding the vertex. But starting with factoring is a good way to go. So here, x squared plus 2x plus 1, I'm going to factor above to leave myself space below. This factors to x plus 1, x plus 1. Or we can write that as x plus 1 quantity squared. And that's helpful for graphing because we can think about it as a transformation. So we can think about the graph of x squared, except it's going to be shifted to the left one. So we're going to go ahead and do a quick sketch here of x squared plus 1. So again, normally x squared goes through the origin, 0, 0, but everything's going to move left 1. And so I'm going to be very careful in plotting my points. So normally the points on x squared, go through 1, 1 and negative 1, 1, but everything's shifted over. And I want to, be even more thorough. I don't really want to sort of rough sketch the graph. I want to be as precise as I can be on these ones. So if I plug in 1, so I can see 1 plus 1 is 2, and 2 squared is 4. So I'm going to pass through 1, 4. And if I plug in 2 next, I'm going to get 2 plus 1, which is 3. 3 squared is 9. And then, of course, due to symmetry, right over here, I know that this point is going to be at negative 3, 4. So I wanted to be as precise as I could, be about this parabola here. So there's x squared plus 2x plus 1. And then I think in this section it is incredibly helpful using different colors. So if you have highlighters or colored pens and you feel like you're a visual learner, then I would recommend using colored tools for drawing your graphs and making each graph a different color. So here, this is a linear function, mx plus b. The y-intercept is positive 3. And the slope is positive 3 as well, or 3 over 1, so we can think about rise over run. So we're going to go up 3 over 1, right? I'm going to do it again, up 3 over 1. So notice we have some intersecting points here, and then I also think about it as down 3, left 1. Again, another point of intersection here. And then I'm going to go ahead and connect these points together for my line. So sketch the region bounded by these two curves. So the region that's bounded by these two curves is this portion here that's trapped between them. So this is the region that we are referring to. And then find its area. All right, so to find its area, we're going to go ahead and need our limits of integration. So those are going to be the x values of the intersection points. So we're extending here from x equals -1 to x equals 2. So we have the integral from x equals -1 to x equals +2. Another reason why I was so careful to graph these precisely. And then we need to know which function's on top and which function's on the bottom. And so here the linear function is on top. And something else that I even sort of recommend doing sometimes is like labeling next to the function. So this one was 3x plus 3, and then this one here was x squared plus 2x plus 1, just to really keep straight which one is which. So we're going to do, again, that top minus bottom, so 3x plus 3. And then minus, and here's where we definitely need to be careful, we need some parentheses. We're going to subtract x squared plus 2x plus 1. And then this is with respect to x, everything here is in terms of the variable x. And so now we have a definite integral that we can evaluate to get the area between the two curves. So let's go ahead and move forward with that. So we have -1 to 2, and then this negative would of course distribute. So we're going to end up integrating -x squared, and then here that's going to be -2x, but plus 3x, so plus x, and then this negative will distribute to the 1, so 3 minus 1 is 2. And we're going to go ahead and find the general antiderivative here with the power rule for integrals, -x cubed over 3 plus x squared over 2 plus 2x, evaluated from -1 to 2 using the fundamental theorem of calculus here. And then of course we plug 2 into everything. So we get -2 cubed over 3 plus 2 squared over 2 plus 2 times 2, all of that minus, and we're going to plug -1 into each x. So we have -1 cubed over 3 plus -1 squared over 2 plus 2 times -1. Just a lot of arithmetic from here, right? So -8/3 plus 2 plus 4 minus 1/3 plus 1/2 minus 2, and skipping some of that, I'm just going to go ahead and tell you that the simplified answer as a decimal is 4.5, or as an improper fraction, right, is 9/2. So the area trapped between these two curves is 9/2. And we found those points of intersection by being incredibly precise with our graphing, and also kind of just getting a little bit lucky that the graphs were sort of small enough and nice enough to be able to find the point of intersection like that. But the other way we could have gone about finding points of intersection, just for reference, is setting the two functions equal to one another, right? So setting 3x plus 3 equal to x squared plus 2x plus 1 and solving that quadratic equation. So that's going to be, let's see, x squared minus x minus 2, subtracting the 3x and the 3 to the other side. And then factoring, we're going to get that x minus 2x plus 1. And then setting each one equal to 0, we get x equals 2 and x equals -1, which we found graphically, right, by again being really precise with our graphing. But we could have also found points of intersection by setting the two functions equal to one another, which we may have to do just depending on the complexity of the graph. Let's look at another example. This time we're just going to set up the integral needed to find the area bounded by f of x equals -1/2 x minus 3, g of x equals -x squared plus 7, x equals 2, and x equals -2. Sketch the region. All right, so let's start by graphing. First, our function f of x is linear, so we have a line in the form mx plus b. Our y-intercept is -3, so let's plot that. And our slope is -1/2, so we can either go down 1, right 2, or up 1, left 2. And I'm going to just extend that across the entire grid that I've been provided here. And I'm going to go ahead and sketch my line. So this was the function -1/2 x minus 3. And then our second function, g of x, -x² plus 7, is a parabola. Now this is a downward facing parabola since the leading coefficient is negative, and it's shifted up 7 units. So our y-intercept is going to be up here at 0, 7. I'm going to go ahead and switch colors. And it's reflected down. So I'm going to go ahead and plot a couple points. And then again, so from here, I am going to plug in very specific points or x values to find points. So if I plug in x equals 2, so 2 squared is 4, but there's a negative there. So -4 plus 7 is 3. So I'm going to have 2, 3, and then on the other side, I'm going to have -2, 3 because of symmetry. And then if I plug in 3, I'm going to get -9 plus 7, so that's -2. So we have 3, -2, and then we're going to have -3, -2, again because of symmetry. And so I'm going to go ahead and connect these points with my parabola shape as nicely as I can here. I missed a little bit. Just make the point bigger. All right, so this was -x² plus 7, right? Or this was called g of x, and the other function was our f of x function. But we also this time have some vertical lines. So x equals 2 and x equals -2 are vertical lines. So we have x equals 2. I'm going to sketch that line here. And x equals -2. So I'm going to go ahead and sketch that line here. All right, so the region that's bounded by all of these is going to be this region here. So I have all of this portion to highlight. All right. So this is the region that we are trying to find the area of. Let me sort of erase this down here. I went a little too far. All right, so this is the area that we're trying to find. And so our limits of integration for the integral we're going to set up are going to extend from x equals -2 to 2. So that's where this region lives in terms of the x-axis. So I'm bounded by these vertical lines. So -2 to 2 is how I'm going to start to set up my integral. So I have x equals -2 to x equals 2. And then we are going to do the top function minus the bottom function. So the top function was the parabola -x² plus 7. And then we're going to have minus the bottom function. That was the line -1/2 x minus 3. And this is all with respect to x, so dx is the differential. So this is the setup of the integral needed to find this area that's bounded by, this curve, this line, and then these two vertical lines here. Now, just as a bit of a note, I do tend to be a little bit formal, especially when starting out, and labeling the limits of integration with the variable, so x equals -2 and x equals 2, really just to help us remember that these should be x values from the x-axis, since our functions are in terms of x and we're integrating with respect to x, but it isn't actually necessary because the differential, of course, implies that these are x values. The other thing that I want to mention is that because these functions had different names, so this function was f of x and this function is named g of x, we could have had a little bit of a shortcut here, and we could have actually written this kind of nicely as the g of x function and then minus the f of x function, still with dx. But in terms of a setup, that would have been perfectly fine because these functions have two different names. So we can just use the name of the top function minus the bottom function. In this example, we're going to set up the integral to find the area bounded by f of x equals x cubed over 3 minus x, and g of x equals x over 3 between x equals -2 and x equals 3. And we're going to be sure to sketch the region. So the two functions that we're looking at here are, one is cubic and the other is linear. So let's start by graphing the linear function just because that's a little bit easier to do. This is of the form y equals mx plus b, but the y-intercept is 0. And my slope is 1/3, so I have a 1 there in front of that x. So I'm going to go ahead and plot the y-intercept at the origin 0, 0, and the slope is 1 over 3, so we'll go up 1, right 3, and then I'll also go down 1 and left 3, and we'll connect those points together. So that is my linear function here. So this is g of x, this is x over 3 or 1/3 x. And then let's go ahead and take a look at f of x, which as I said is a cubic function. So what we should know about a cubic function is at the very least, what x cubed looks like. So just a little quick review up here off to the side. We know that y equals x cubed as one of our basic functions looks like this. So the right side points up and the left side points down because my leading coefficient is positive. So that's going to describe the end behavior. Now, x cubed over 3 minus x is going to have the same end behavior, but some different stuff is going to happen in the middle. So to determine what happens in the middle, we should try to find our intercepts, right? So we should try to set this function equal to 0. So I'm going to go ahead and do that work over here off to the side. I'm going to set my function equal to 0. So I have x cubed over 3 minus x. I'm in search of my x-intercepts. So I'm going to factor out an x from each term here. So if I factor out an x, I get 1/3 x squared minus 1. And now I can use the zero product property and set each of these equal to 0. So in other words, I have x equals 0 is an x-intercept, and then 1/3 x squared minus 1 equal to 0. So here I have 1/3 x squared is equal to 1. I'll add the 1 to the other side. To get rid of 1/3, I'll multiply by 3. So I get x squared equals 3, or x equals plus or minus the square root of 3. When I take the square root of both sides of this equation, plus or minus is going to come out with the square root of 3. So we have 3 different x-intercepts for this cubic function here. So we have the origin, and then we also have positive and negative radical 3. So positive and negative radical 3, or positive radical 3, is between 1 and 2, right? So the square root of 4 is 2, so it's a little bit less than that. So I'm just going to, approximate it here. This is the square root of 3. And then the negative 1 on the other side, right? Negative radical 3. And if my end behavior, right, is that the right side has to go up, and then this left side has to go down, I could just do a little bit of a sketch here, and create my function, my cubic function, f of x. So f of x was that x cubed over 3 minus x. Now, I do know what's going to happen with this setup, obviously. So when I graphed this, I was a little bit more accurate than I necessarily know from the information given. I made sure that my two functions were going to intersect at -2 and +2. Now, how did I know that? Because I know that when I set these two functions equal to each other, I'm going to get those two values out. Well, I haven't done that work yet, so let's go ahead and do that work and confirm what my sketch gave us. So if I set x cubed over 3 minus x equal to x over 3, well, on this equation, I can go ahead and clear fractions just to not have to deal with them. I could have done it over here too, but here I'll clear fractions, multiply everything by 3, so I'll end up with x cubed minus 3x is equal to x. And then I'll subtract the x to this left-hand side. So I have x cubed minus 4x is equal to 0. When I solve equations, I always want to get everything to one side, set it equal to 0. I'll factor out an x. So I get x squared minus 4 left over, and x squared minus 4 is the difference of squares. So I get x, x minus 2, x plus 2 as factors. So we get 3 different values out of this. If I set each part equal to 0, I get x equals 0, I get x equals positive 2, and x equals negative 2. So when I had sketched my cubic, as I said, I knew what I was going for. I know that they intersect at negative 2 and positive 2 as well as 0. So if you had just drawn a little bit more of a rough sketch for x cubed at first, and maybe made them intersect over here or a different point, you can always go back and correct that after you set your two functions equal to one another. So now we have to go ahead and make sure we take into account these two vertical lines, x equals negative 2 and x equals positive 3. So x equals negative 2 is right over here. Let me go ahead and sketch that. That's a vertical line, right? Also happens to be a point of intersection, but x equals 3, that's not a point of intersection, right? So x equals 3 over here looks like this, right? And so this graph continues on, it continues up, and it will then, intersect this at some point. Now, do I have to know exactly what that y value is? I don't. I don't need to know exactly what that y value is, because when we set up our integrals, we're using x values. So I need this negative 2 value, 0, I'll need positive 2, and I'll need x equals 3. So why am I going to need all of those different values? Well, because the top and bottom function switch. So in order to really clearly see that, I'm going to shade the region that we're trying to find the area of. I'm trying to find the area trapped between these two curves and also bounded by that x equals negative 2 and x equals 3 line. So we're actually trying to find the area of like 3 different regions. And as I said, those regions, they have a different top and bottom, right? So it kind of flips back and forth. So what that means is this set of instructions wasn't quite accurate. It's not just set up the integral, it's really set up the integrals that are needed to find this area bounded by the curve. Because we always need to do top minus bottom, but for this area, it switches. And so this is where it can be very helpful to label the graph a couple different times actually, and like close to the region. So this purple graph is f of x, right? So here's f of x, here's f of x, and then the blue graph, the line, was g of x. So in other words, how do we find this total area? We're going to set up the following integrals. We're going to say that this area is the integral from x equals negative 2 to x equals 0 of top minus bottom, so that's f of x minus g of x dx. And then plus, so we're going to have this separate region, and that's going to extend on the x-axis from x equals 0 to x equals 2, that next point of intersection. So we have 0 to 2, and the top and bottom switch, so g of x minus f of x dx. We definitely need that differential all the time, especially since here we didn't write x equals, so that's going to imply that these are x values. We always need the differential. And then finally, we have this other region here. It's sort of open-ended, right? It's going to close off at that vertical line, x equals 3. So it starts at 2, ends at 3, and the top is the cubic, f of x, and the bottom is the linear function, g of x dx. So this is a setup of the integrals needed to find the area bounded by these two functions and then these two vertical lines. In this example, we have set up the integral or integrals needed to find the area of the region in the first quadrant that is bounded above by y equals the square root of x and below by the x-axis and the line y equals x minus 2. So here we actually have the graphs given. So the square root function is this curve here. So I'll go ahead and label that. So that's the square root of x. And then we have the blue graph here is the line x minus 2. Now let's go ahead and highlight the region, being really careful because the instruction said that the region is in the first quadrant only. So it's in the first quadrant, bounded above by the square root of x, and below by the x-axis and the line y equals x minus 2. So the region that we're talking about here is this one. So we have this little enclosed region in quadrant 1. All right, so how are we going to set up the integral or integrals needed to find the area of this region? Well, again, I really stress, especially if you're a visual learner, using different colors, using highlighters, because we always want to make sure that we have the top minus bottom across the entire region, the same top and the same bottom, because if it switches, then we're going to need multiple integrals. So if I look at this region here, starting off at 0, the top function is the red function, the square root of x, and the bottom is just the x-axis for a little while, right? All the way up until x equals positive 2. So that means we're going to have one integral to find the area of this first part here. And so that first integral is going to look like the integral from 0 to 2 of the top function, which is the square root of x, and then minus the bottom function, which is really just 0. The x-axis is the function y equals 0. So there's really kind of no bottom function, right? It's just 0. So it's your standard definite integral. So the square root of x, just dx. Plus, and then we're going to go from 2 to this point of intersection here, the x value of the point of intersection, as my limits of integration, and then we're going to have top minus bottom. So the top is still the square root of x, but the bottom is the function x minus 2. So our next integral is going to extend from x equals 2 to 4 of the top function, the square root of x, minus the bottom function, x minus 2. We want to make sure to include parentheses because that negative would distribute around that second function, x minus 2. So here, again, we just want to be careful about clearly reading the instructions, that we are in the first quadrant, and we're bounded by the square root of x on top and below by the x-axis and the line x minus 2. And not kind of just, sometimes people just want to fill in a little bit more than they see, or a little bit more than they're told, and so just going by what they see, and a lot of people will fill in this little triangle shape down here. So we just really want to be careful about reading the instructions. The other quick thing I just want to mention here is that these are some pretty basic graphs, and we do know very specifically that the square root of x passes through 4, 2, so that really is a point of intersection. We never want to eyeball it and just, oh, that looks like it's about 4. We do know for sure that it's 4, and we could have confirmed that by setting the two functions equal to one another. So if we were to set x minus 2 equal to the square root of x, we would have to square both sides. So we'd have to do x minus 2 squared is equal to x. We'd have to distribute this out on the left. So x squared minus 4x plus 4 is equal to x. Remember, this would have to distribute out. And I'd subtract the x to the other side. So x squared minus 5x plus 4 equals 0. I always want to set equations equal to 0. I'm going to factor this quadratic. So it's going to factor to x minus 4. X minus 1 is equal to 0. And so we're going to get x equals 4 and x equals 1. Now you might be thinking, where's x equals 1 coming from, right? These two graphs don't intersect at x equals 1. But what's happening is when we had to square both sides in order to solve this, the square root function was completed into the full sideways parabola. And so the other, reflection part is down here was kind of taken into account when I squared both sides. And that's where that x equals 1 is coming from, right? So we kind of just have to be careful. Sometimes the techniques that we use to solve equations create what are called extraneous solutions. So that value didn't make sense in terms of the problem that we were solving. But again, on a graph this basic, we can go ahead and use the values that we see because we know for sure that those are exact values. We don't want to approximate.